You have ice in a cup, it's hot outside, you realize your ice starts to melt. After a couple minutes, your ice completely melts. This is due to thermodynamics, which is the relationships between heat and other forms of energy. Um, Today I will show how heat and thermal energy affect physical changes conceptually, while I also demonstrate through algebraically. Key terms include heat, which is energy being transferred, temperature, which is just the measurement of kinetic energy of molecules, and thermal equilibrium, which is just basically means being at the same temperature. In order to actually calculate heat, the transfer thermal energy, we first have to find that heat equals Q. And the way you find it is Q equals m times C times the change in temperature, mass of the object, specific heat capacity, and the change in temperature. Specific heat capacity is actually the amount of energy needed to raise 1 kilogram to 1 degree Celsius. So the way heat is actually measured is different when you're going within a phase versus when you're doing it between a phase. So within a phase, heat is calculated like normally how we said, m times c times change in temperature. So, but when we're going between a phase, it's calculated as q equals m times l latent heat. Between a phase, we mean like melting, when it's actually switching, and heat is calculated differently. L is latent heat, which has two variations, LF, which is latent heat of fusion, and latent heat, LV, latent heat of vaporization. So you use it in when you're going from different phases. Now there's two different ways heat is transferred. One is endothermic and the other is exothermic. And within a phase, endothermic temperature goes up, potential energy goes up, and motion and vibration goes up, while exothermic temperature goes down, potential goes down, and motion vibration goes down. Between a phase, when such as melting, it's different. Temperature does not change. Potential energy, however, increases, and this breaks IMFs holding molecules together. This brings me to the first law of thermodynamics, which is the law of conservation of energy, which is seen in endothermic between phases, where where it's changing from phases, temperature doesn't go up, kinetic energy doesn't go up, but potential does. So this is showcasing the conservation of energy. Now we're here at the lab using a heater to heat up um, water with ice, which goes from ice to water, as seen right now, to finally boiling, which is seen right now. And I will show how you can show this algebraically. Now this is a graph showing previously algebraically what was being transferred heat-wise between phases and within phases, and as you can see, it's different. Now moving on to thermal equilibrium, this means being at the same temperature, Q plus Q equals 0, subjects reach equivalent temperature. Q, ice, and you have a Q of H2O. Let's say the ice is 1 degree Celsius and the water is 30 degrees Celsius, and you mix them, they reach an equivalent point of 20 degrees Celsius. By using data from a class, we can calculate the specific heat capacity of a metal by plugging everything into this equilibrium formula. And we found the specific heat to be 447.7. Enthalpy. All molecules have a standard enthalpy of formation, which is the amount of heat required to raise or lower the potential energy of a system. So if it's positive, that means potential energy is going up, which breaks IMFs holding together. And if it's lower, if it's negative, that means IMFs are being strengthened. Lastly, I want to talk about the second law of thermodynamics, which is entropy. And entropy just means disorder, and an increase in entropy is increase in disorder. Um, Usually how we define this is going from solid to liquid to gas is an increase in disorder, and going from smaller molecules to bigger molecules is also an increase in disorder. So in our laboratory experiments, when we go from solid to gas, solid to liquid, we have an increase in disorder, and if it was the other way, it would be a decrease in disorder. So the second law of thermodynamics says that the universe the entropy of the universe is constantly increasing because the universe itself is always increasing. So we can't. Everything becomes bigger, and more molecules are being created.